all, I would like to introduce what is the Runge-Kutta method. Did you guys know what is Runge-Kutta method? Runge-Kutta method is in numerical analysis. Runge-Kutta method are a family of implicit and explicit iterative methods, which include the well-known routine called Euler method. This method is to solve the ordinary differential equation, which is ODE, that has better approximation than Euler method. So it's basically to solve the ODE that is more accurate than the Euler method. We are fine for the fourth order approximation. First, Euler's method was derived from the Taylor series as yn plus 1 equals to yn plus hk1, where k1 is equal to fxn yn. Xn and yn is normally the initial condition that given in the equation. It also generally represented by x0 and y0. And the equation also gives the step size, which is h. And then looking for the second method, it is described by the formula of yn plus 1 equals to yn plus h over 2 k1 plus k2, where k1 and k2 is the represented by formula as function xn yn, where we know that the k1 of xn yn is the initial condition. So k2 is function of fxn plus h yn plus hk1. So if we had the second or the third order equation, where Arcade third method is same as the Hens method, where both of them are the third order method. It is similar to Hens method, it's just that yn plus 1 equals to yn plus h over 6 k1 plus 4 k2 plus k3, where k1 and k2 are same as the previous one, while the k3 is fxn plus h yn minus hk1 plus 2hk2. And then the last order is the fourth order, where it's known as RK fourth method. The RK fourth method is yn plus 1 equals to yn plus h over 6 times k1 plus 2 k2 plus 2 k3 plus k4, where all the k1, k2 and k3 is like before, but the number of h depends on the order. So the k4 is equals to xn plus h yn plus hk3. So that's all from the first paper is from the Banish Moulavi Arabashi, which is the state about the application of Runge-Kutta numerical method to solve Runge equation for hydrogen and positronium atoms. So this paper is to find the hydrogen and positronium atom from Schrödinger equation, where this is the equation for atomic mass and potential voltage, and this is equation for one-dimensional potential equation. So this is the equation for the hydrogen and positronium. A is for the hydrogen atom and B is for the positronium atom. So we use the Runge-Kutta method. So this is the equation for the Runge-Kutta method. We obtain the Taylor series expansion of yxn plus h up to fourth derivative order and Taylor expansion for function with two variables, K2, K3, and K4. And then we put the results in the yn plus 1, which is yn plus ak1 plus bk2 plus ck3 plus dk4. And then with comparison of two expansion, we reach to 9 equation with 13 unknown, and local error is order. Then choose 4 unknown as the desired unknown, and 9 other unknown are calculated. So at the end of the calculation, the answer is given as stated here. So at the end of this paper, computer program for Runge Kutta method for fourth order that has been used in numerical computation is presented. So this is the result based on the Runge Kutta method for the ground state wave function of hydrogen and positronium, and the present probability function for the figure 2, while for the figure 3, it is the present probability function for atom of hydrogen and positronium in the column potential well. So, in conclusion, numerical Runge-Kutta method is to solve differential equation in physics. It's very efficient and accurate and very effective, and it is also useful for solving problems physics. Numerical results from this study are good agreement with analytical calculation for hydrogen atom, result in modern physics and quantum mechanics. This method can be used in the analysis of quantum system with different potential.
Next, we will be talking about an article written by Muhammad Faris Fatoni and Aji Ida Wiryandi with the title of Comparison between Euler-Runge-Kutta Adam Molten Integration Method in Particle Dynamic Simulation. As for introduction, simulation is a process of imitating the real system for the purpose of studying the behavior of the system, and computational simulation is a simulation which imitates the behavior of a variety of particle physics such as solidification. And then another important key is numerical integration method, where these affect the performance of the simulation. Particle dynamic simulation basically is a process with imitating the movement of particles in real life, which follow the Newton's second laws, F equal to ma. And the particle dynamic modeling will compute the particle acceleration, particle velocity, and also the particles' positions. Generally, the physical simulation process will consist of: first, it will compute acceleration vector from the force vector, and then integrate the acceleration vector, which obtain velocity vector. That velocity vector will be integrated to obtain the position vector. At last, we can compute the impulse force due to collisions. This is the particle dynamic simulation flowchart, where you can see here where it computes velocity vector of particles using the 4 integration method. And this is the 3D simulation of experimental result using Microsoft Visual. Then, to be more clear, this is the comparison table, which you can see the Euler have the least average computation times in seconds. So as a conclusion, Euler method is faster and it is switchable for smooth motion of particles, where Runge-Kutta method is easier for programming and it's stable for all the particles. And Adam-Bashford Molten method is only suitable for extreme abrupt motion of particles. So this is all from us. Thank you for watching the Numerical Method shows.